Good morning everyone and welcome to the NPTEL course Advanced Distribution System Analysis and Operation. We are continuing with our module 4, that is Distribution Network OPF Analysis. We have done single period and multi-period OPF, developed the problem and also solved the problem. So today we will see that uncertainty quantification and overview of probabilistic OPF. We will start this topic and we will see what it is and how we can develop the OPF problem. So till that point, whatever OPF problem we have developed, the input parameters we considered as to be a fixed value. That means we know that value with a 100% confidence level. Okay. But that is not the case whenever you go for DER generation or loads or any kind of input parameters, because DER generations are not fixed, they may be uncertain, they may be not, they are uncertain. So, if you take those uncertainty into account, then you cannot go with the deterministic solution method. So, when you know the input parameters with a 100% confidence level and you developed your OPF, that is called your deterministic OPF. But when you consider the uncertainty along with your OPF model associated with your input parameters and you developed your OPF according to it, then it is called a probabilistic OPF. That means that will deal with the probability value of your uncertain events, that what is the probability of occurrence of that uncertain events. So, incorporating this uncertainty as a random events, your probabilistic OPF is generally formulated. Okay. So, unlike deterministic optimization, probabilistic optimization technique discovered the best solution for data with randomness. So, it will find out the solution which has best solution considering the randomness in the input data. So, how to process with the probabilistic OPF? First, you define the objective function and the constraints like we did for the deterministic OPF as well. Identify the uncertain input parameters, that may be your DERs or loads or whatever. Then represent their uncertainties or the randomness as a probability density function, a suitable probability density function, and obviously that will be a complex continuous function. So, you cannot deal with that continuous function in a discrete OPF framework, because our OPF frameworks are all discrete, we are dealing with summation of t. So, that is a discrete framework. So, if you deal with the discrete framework, you cannot go with this continuous. So, first you have to discretize it, right. So, generate scenarios using sampling techniques from those PDF methods. Okay. Then solve the deterministic optimization problem for each scenario and record the output. So, let us say with this you got 100 scenarios, for that 100 scenarios you solve your deterministic OPF for those 100 scenario inputs, and then combine all the outputs with the statistical measure. So, after combining, what you will get, that you can say that is the output of my probabilistic OPF. Okay, got it? So, what are the uncertain OPF input quantities? We can see first, obviously the power generation from the solar power panel. Second, active power generation from the windmills. These two things are obviously your uncertain thing. Any renewable energy generation is your uncertain. Demand, because you do not know how your customer will behave, how much they will consume. So, electricity demand is also uncertain. Energy purchase price, because you do not know that what will be the energy purchase price for tomorrow. You can guess it obviously, but that is not 100% accurate. That forecasted data is not 100% accurate value. And your electric vehicle demand, that means how much electric vehicle is going to penetrate in your distribution network, or how much demand is coming in the next days, so that you cannot predict properly with a 100% confidence level. Okay. So, these are the uncertain input quantities for your OPF problem. So, now how to model that uncertain quantities? The all uncertain variables are represented by a probability density function. Okay. The PDF of the ith uncertain variable is fxi for the uncertain input parameter. Let us say it is fxi. So, the state probability you can calculate for a discrete state S having the probability density function Fi xi. So, the probability P corresponding to that state for being to that state, that means your probability of being to that state is actually the integration of the lower limit to the upper limit of your probability density function. Okay. This integral will give you the probability mass for that state, and if you get the probability, then you can act accordingly for developing your probabilistic OPF. So, the state representative value, this representative value xis, that means for that value of that state for each discrete state is calculated as the midpoint of the interval. That means, if you have a lower limit, if you have an upper limit, then average or midpoint of that limit you can say at the, that is the highest probability, that value has the highest probability of occurrence. Okay. So, keeping that, which kind of probability density function you can use for different uncertain parameters. First, we will see solar power generation. The solar power generation is normally represented with the beta probability distribution function. So, you can see this is your beta probability distribution function and this is the equation of it. Now, why beta? Because beta probability distribution function says that it can go from minimum 0 value to maximum 1 value. Value lesser than 0 is also not possible, value greater than 0 is also not possible. The same pattern we will see for solar power generation as well. The value of solar power generation is either 0 or it can be at the maximum value. So, probability of both the things for a particular time, let us say you are at your 12 p.m. noon. So, there is a very low probability that at 12 p.m. noon you will get 0 power generation from your solar panel. Similarly, there is a very low probability that you will get highest power generation at your solar panel at the 12 p.m. because some clouds can come, it may be a cloudy day or rainy day. So, highest probability, lowest probability is there for highest power and as well as lowest power. So, depending upon that, your solar output is bounded between your minimum and the maximum. So, somehow your highest probability occurrence event or the point is at the mid of these two, depending upon how you are selecting this shape parameters or your mu and the standard deviation value, that is your mean and your variance value. Okay. So, depending upon that you will shape your alpha and beta, and upon choosing alpha and beta you can give a proper shape to your beta probability distribution. Okay. Now comes to the wind power. So, the probability density function for wind power generation describes the likelihood of the different power outputs from a wind turbine influenced primarily by the wind speed variability, that we have seen that it is actually P is proportional to V cube. So, the variability in the wind speed is actually the variability at your wind power generation. So, generally the wind speed is modeled with the Weibull distribution, which is represented by this equation where lambda and k are scale and the shape parameter. Depending upon that you will get the V value, and if you put that V value you will get your power with this equation. We studied this equation before as well. So, the scale and the shape parameters also you can define with this standard deviation or variance value and the mean value, but solving this equation you can have to use the numerical method. So, by defining the scale and shape parameter, again you can select which Weibull distribution, what is your shape of your Weibull distribution for the uncertainty. Okay. If you want that your highest probability will be very high, that means your prediction value, your forecasted value has the very high probability, you can go with this, that for a certain event your probability is very high. But if you are not that much confident, so the tail, you can see the tail of that Weibull distribution is not very long, very short tail. That means you are very confident of your forecasted data. But if you are not very confident, then you can take this flattened curve Weibull as well. So, that will give you a long tail for long range of weighable distribution or long range of wind power variation. Okay. So, depending upon your lambda and k value suitability, you can choose which weighable distribution or what is the shape of your weighable distribution. Then load and the energy price. Generally, load and energy price is represented with the normal probability distribution, because your energy price can reduce or enhance, even your load also can reduce and enhance. So, it has the provision that it can go to the negative direction as well, and it can go to the positive direction as well. So, that is why we take this normal distribution function by taking that your forecasted value as the mu and a certain value of your standard deviation. Okay. But how much tail you will take for that normal distribution? That is a question. So, you know that theory that 60% of the data falls under mu plus sigma plus minus sigma range of the normal distribution. If you little bit flatten it, then for mu plus minus 2 sigma, total 95% of the data comes, and for mu plus minus 3 sigma range, almost entire data set will come. So, for probabilistic distribution function, for probabilistic OPF development, generally we take this mu plus 3 sigma to mu minus 3 sigma range and do our operation or our uncertainty. We take that it is ranging from this point to this point, that a wide range of uncertainty we can consider, and your solution will be more and more effective for a longer variation of your randomness. Then we come to the EV parameters. There are 5 different parameters in electric vehicle itself which are uncertain. First, how much distance it travelled for the entire day when it is on the road. Second, number of electric vehicles arriving at the charging station. Third, when it is arriving at the charging station. Fourth, charging duration, that means depends upon the car battery or depends upon your charging port, how much time it is taking. It can take 30 minutes, it can take 1 hour, it can take even 4 hours. So, how much time it is taking, that is also your uncertain parameter. And at the last, at which SOC level that electric vehicle is coming. That means what is the battery level, energy level of your electric car. So, generally the driving distance for electric vehicle is often positive and it is skewed. So, for that generally it is modeled as log normal probability distribution function, which is looks like this. The mean and standard deviation of that log normal distribution function is normally not equal to your actual driving distance mean and standard deviation. It is calculated from the daily driven distance mean and standard deviation using this log normal formulation. You will get your mu d and sigma d, then put it here and fit into a log normal PDF for getting the uncertainty in the distance travelled by an electric car. Okay. Then number of electric vehicles arriving at a charging station is generally modeled with the help of Poisson distribution, because you have to count. So, that counting is uncertain. So, if you take that counting uncertain, you can model it as a Poisson distribution. Okay. So, this is your Poisson distribution curve where lambda is the average number of car arrival per unit time. Then your electric vehicle arrival time and charging duration you can model as a normal PDF, because that has also a negative and a positive. You thought that it will arrive at 5 p.m., but it can come at 4:30 or it can come at 5:30 as well. So, if 5 p.m. is your mu or the standard your mean value, then your normal probability distribution function can go from negative side of it to the positive side of it. Okay. Same for your charging duration. You thought it is 1 hour, but it can be 2 hours or it can be half an hour. Okay. So, that is why we normally take normal probability distribution function to represent the uncertainty with EV arrival time and charging duration. And SOC boundation, again it is same as your PV generation, that either it will be 0 or maximum it can go to 1. It cannot go more than 1, because battery has a certain limit. So, SOC has 1 per unit limit. You cannot go beyond that. Even SOC can not be decreased below 0. That is physically not possible. So, if that is the case, so it is best suited for the beta probability distribution function. Okay. Now, you got a continuous probability distribution function for each and every uncertain parameters, but you cannot fit that continuous function to your discrete optimization portfolio. So, what you will do? You have to generate the samples out of it. So, scenario generation by sampling technique is the next process for the probabilistic OPF design. So, computation feasibility you will get continuous distribution have infinite outcomes. Generating discrete scenarios allows practical simulation and optimization. Okay. Scenarios capture possible real world variation in uncertain inputs, and that will give you the uncertainty representation. Robust decision making, scenario based models help evaluate risks and make decisions that perform well under uncertainty. That means, you will have a large variation of the scenarios in hand, and you can see when your network or when your power system is operating in the most efficient manner and at the worst condition as well. Both the things is in front of you if you have an uncertain event. So, that you will get by the scenario generation. Then probabilistic constraint also you can handle with the help of generating the scenarios. So, normally 3 different algorithms are followed for scenario generation. First is the Monte Carlo simulation, which generates huge number of scenarios to get the proper decision. Then you have Latin hypercube sampling, which introduces or generates lesser number of scenarios compared to the Monte Carlo simulation. And then you have point estimation method, which generates only 2, 3 or 5 number of scenarios, and it will give you the solution for the entire randomness. Okay. So, first we will see what is Monte Carlo simulation. So, it is a very simple method and it is used for generating large number of random samples. It will not work if you generate only 2 or 3 samples. It is the range of that sample is around 1000 to 2000. You have to generate 1000 to 2000 samples from each and every probability distribution function to catch the actual variation in the Monte Carlo simulation. So, why it is so? That will achieve you to the good accuracy. Now, you will see the algorithm. First, you will define the probability density function for that uncertain variable x. Okay. Then define how many samples you want. A higher number of samples will improve your accuracy. Then generate that number like n number of values between 0 to 1, which is uniformly distributed. You generate random numbers, okay, between 0 to 1. That will give you the cumulative probability value, cumulative probability density function value. Now, you do the inverse. That means, you have your fx value. Now, you will do, and this is for your p, let us say. So, your x is f inverse of p. So, you know your probability by generating the values between 0 to 1 randomly. That p values you will put here and you will get the x. So, that you will get by doing the inverse of the cumulative distribution function for the corresponding probability distribution function. Okay, got it? And then you will get the random samples of the target distribution. So, construct the scenarios, each sample value xi, and then you will get the scenario for the entire horizon. So, each samples will have the probability of maximum 1 by n unless a same sample has been generated multiple times. If a same sample has been generated, so depending upon the frequency of its generation, you can adjust the probability values for that particular sample. Okay. So, this is very simple method to generate scenarios from a probability density function. Just you need to take random values for the probability, do the inverse of the CDF, and you are good. You will get your scenario. Then the next sampling method is the Latin hypercube sampling method. It is a statistical method used to efficiently generate random samples from a multivariate probability density function. So, you have to remember, Latin hypercube you can only use when you have 2 or 3 uncertain parameters in your problem, not the single. If you have a single uncertain parameter, then you have to go with Monte Carlo simulation. But if you have a 2 or 3 uncertain parameters, then you can go with the probability density, your Latin hypercube sampling method. So, what it does? LHS ensures better coverage of the input space with fewer samples compared to your basic MCS, thus reducing the computational cost. So, in LHS reduce the computation cost for your Monte Carlo simulation because it generates lesser number of scenarios from the probability density function, and it will also ensure no clustering. How? That we will see now. First, you will define your PDF same as your Monte Carlo simulation. Now, you divide each and every cumulative distribution function into equal intervals. That means, if this is your CDF, let us say this is your CDF, then divide that CDF in equal number of intervals. That means, this is equal to this, these two are equal, this is equal to this is equal to this, equal interval you segregate it, okay, n number of, you can take different depending upon how many scenarios you want, okay, how many scenarios you want, that much number of segregation you will do with the CDF. Now, from the each interval randomly select a scenario by inversing the CDF. The same thing we did for the Monte Carlo. So, from this interval, let us say you will take only one randomly. From this interval you will take one, from this interval also you will take one. So, total if you have n intervals, so you will get n number of scenarios, and that this n number is very lesser compared to your Monte Carlo simulation. Okay. So, as you are taking different intervals and then you are selecting your scenarios, so clustering the scenarios to a specific area is reduced, which is there for Monte Carlo, because Monte Carlo you are taking it randomly. So, it is possible that you took the entire data from only this part or only from this part. So, you get biased solution. To avoid it only, we will take large number of scenarios that it will cover the entire horizon. But as here in the Latin hypercube, we are already segregating into multiple intervals. So, at that time and taking the one scenario from each interval, so we can say the representation from each interval is already there. And if the representation is there, that means you have good, wide, vast and diverse number of scenarios from the entire probability density function range. Okay. Then use the sample values of each variables are randomly paired across variables to ensure stratified and non-redundant combinations. That means you have multivariate uncertainties. For each variable CDF you have generated 10, 20 or 100 number of scenarios, then you do the combination. That is why we told that it is only workable for multivariate problem. So, you do the combination and you will get a huge number of pair combination of uncertain events or uncertain scenarios. Then that will give you a paired values of all variables to matrix form. Then you use that scenarios for your probabilistic OPF formulation. Then the last method of scenario generation is the point estimation method. What we do with the point estimation method? Point estimation method transform continuous probability density functions of uncertain inputs into a few representative points. That means it will cluster, or it will, you can say it will cluster the entire problem or entire probability density function to 2 to 3 points or 5 points. That means it will collate the entire scenario to only 2 to 3 representative points for the entire probability density function. And it will also give you the associate weights, which capture the essential variability and the statistical properties for that random event. So, it is a very computationally efficient because you are generating only 2, 3 or 5 number of scenarios and need fewer evaluation points compared to your Monte Carlo simulation and Latin hypercube simulation. So, it is normally proposed by Hongs, and it is a 2-point estimation method which is very popular for the scenario generation and OPF analysis, where each random variable is approximated with 2 concentrated scenarios only, okay, and their corresponding weights. Let you have a vector z and a function f, where you have m number of uncertain input. So, z vector is represented by a function f, where is p1, p2, pi and pm all are your random events, and you have total m number of random events. So, for the lth input or for the lth number of uncertain variable, the two concentrated points you can calculate it like this, where this is your actual concentrated point, this is the mean of the probability density function, this is your standard deviation, and you have a beta constant value, that is called the standard location, okay, that you can calculate from this equation. And weights you can assign for each and every concentrated scenario. So, you can see the k is varying only for 1 and 2. That means, for a particular uncertainty L, you have only 2 concentrated location. Okay? Correspondingly, you have also weights as well. So, this beta value will be calculated with this alpha, and it is dependent upon the third central moment. You will calculate the third central moment for doing the 2-point estimation method. So, depending upon which point estimation method you are adopting, that accordingly you have to change that central moment calculation. Okay? So, there is a comparison table of it. You can see the sampling nature. Monte Carlo simulation is random sampling. For Latin hypercube, we will take stratified random sampling. That means, we are doing it in a very good manner, and for point estimation we are getting the deterministic point estimation method, fixed number of points. Scenarios, you have to generate large number of scenarios for Monte Carlo simulation. Comparatively, you have to generate lesser number of scenarios for Latin hypercube, and only 2 to 3 points you have to generate for point estimation method. That means, your computation complexity is very low if you adopt point estimation method. Computational cost is very high for Monte Carlo, moderate for Latin hypercube, and very low for your point estimation method. However, the accuracy is very high for Monte Carlo simulation, because other than concentrating it or intervalling it for multiple events, you are taking the entire randomness. If you take it, then obviously you are more close to your accurate result. So, that will give you the higher accuracy. So, Monte Carlo simulation always possesses you higher accuracy. Similarly, Latin hypercube also gives, but it is lesser compared to the Monte Carlo simulation, and you will get moderate accuracy for point estimation method. Convergence, obviously you are dealing with 1000 scenarios, so convergence will be slow for Monte Carlo, faster than MCS for Latin hypercube, and point estimation method is not even stochastic. You just evaluating your randomness only for 2 points. So, obviously it is very fast, okay, and almost it is a deterministic problem. So, it will directly handle the PDF, it will handle the ensures the uniform marginal coverage, and it will using the central moments, that may be mean, variance, skewness, third moment, like this. Monte Carlo is very easy to implement. Latin hypercube and point estimation method is you need a little bit more calculation, as we have seen, for getting the scenarios. Okay? So, use cases are very high, like Monte Carlo simulations are normally used frequently compared to these two methods because of its higher accuracy. Okay? Reproducibility low, because you are generating 1000 random events. Okay? So, again let us say you took a normal distribution function and now you are generating 1000 scenarios. There is very lesser chance or almost zero chance that tomorrow if you again generate 1000 scenarios, those 1000 scenarios will be same as what you generated yesterday. That is never going to happen. Okay? Or if it has happened, then only you will say within thousands only 2-3 samples or 10 samples are same. Okay? So, the reproduction of the same sample is very low in the Monte Carlo simulation. In Latin hypercube, the probability will be little bit higher because the intervals are same. So, maybe you will get, maybe it is not 2, 3, it may be 50 or 40. Okay? So, it is higher than your Monte Carlo simulation. But for point estimation, it is deterministic because it will concentrate to its location, mu plus some constant beta and then sigma. So, if it is that, Whenever you do the calculation, you will always get only those 2 points. So, that is a more deterministic point you will get. Now, we will focus on the scenario reduction technique. We have seen that Monte Carlo simulation is the process with higher accuracy, and this is giving you very good results, right. But for that you have to deal with thousands number of scenarios. So, is it really possible to deal with thousand number of scenarios all the time for all time step? And if you have multiple uncertain events, then each and every will give you 1000 scenarios. That is not possible. So, though MCS possesses highest accuracy, but the computational effort is maximum as large number of scenarios need to be handled. So, scenario reduction techniques are used in the Monte Carlo simulation to limit the computational burden while retaining the most representative scenarios of uncertainty. That means, after performing Monte Carlo simulation, you add a scenario reduction technique that will reduce the redundant scenarios and collate them with their most nearest, or you can say equivalent scenarios. That will reduce the number of scenarios you are dealing with. Since NCS can generate thousands of scenario, reduction helps make stochastic optimization more tractable. So, generally 5 different scenario reduction techniques are used: forward selection, backward reduction, k-means clustering, fast forward selection, and optimal scenario reduction. So, what is forward selection algorithm? Forward selection algorithm starts with a empty state. That means, you do not have any scenario selected. Now, from the original set of generated by your Monte Carlo simulation, you pick up one by one and then transfer them to your new set value. So, how you can do it? First, you have your original set with a scenario probability value, and you have your reduced one where you want to put them. So, this is your reduced number k, which is lesser than your n. So, at first your reduced set has 0, that is a null vector. Okay. Now, you will calculate the Euclidean distance between all the scenarios present in that original set. Okay. Then calculate pairwise distance for all of them. Choose that scenario which has the weighted average distance of the minimum value, okay, which is as the minimum value, that you add that scenario, pick up that scenario and keep it at the new set, reduced set 1. Okay. After that, again you select the original scenario, okay, and there you calculate the distance between the each scenario in the original set and the current subset. That means, which points are there at your reduced set. Now, you see that how much they are close with their original set, and those points in the original set which are closer to that reduced set, you take those one and move them to the reduced one. Okay. And then for each full scenarios, assign the nearest scenario to the SRED. Okay. So, whatever scenarios have nearest probability or nearest distance with your reduction state values, there you just adjust that their probability with the reduced set, and then you will get a reduced scenario probabilities, and you will get a reduced set for your forward selection. So, total number of scenarios you can reduce from 1000 to let us say 100 or 200. Okay. So, this is a forward selection where it starts with an empty set and incrementally adds scenarios in the reduced set. Okay. So, at each time step, the scenario that minimally increases the distance from the full scenario set is selected. Okay. Useful when computational resources are limited. That means, first you take the minimum one, add it to the reduced, then you take the minimum distance which is affecting the original set. Okay. You have multiple points in the original set, you see removing whom will give you the minimal distance value or minimal increase in the distance value. Take that value and then move that point from the original set to the reduced set. Okay. And do this process continuously till you reach this k value. When you reach that k value, stop it and take only the reduced set for your further operation and discard all other extra scenarios from your calculation. Okay. Then the reverse thing we do for backward reduction algorithm. Forward selection means you have 0 selected, started one by one adding. Backward reduction says you start with the full scenarios and eliminate one by one. So, what we do? First begin with a large set of generated scenarios from the Monte Carlo simulation and their assigned probabilities. Then choose a distance matrix, typically Wasserstein distance, to measure the closeness between scenarios in the probability space. So, you calculate that distance between different scenarios. Then at each time step identify the scenario whose removal causes the least increase in the overall distance. That means whom you will remove, that will not affect the overall distance of the or this function value of the your remains set. So, identify that point and just remove him, and before removing reassign the probability of the removed scenario to its nearest neighbor. Okay. That means your before removing how much probability it has, that probability you add with its nearest scenario value, then that scenario probability will increase obviously. So, then again you calculate that distance value for the entire set value, then again identify that point whose removal will not affect that total value, then remove him and you assign the probability with its nearest one. So, do this process iteratively until your total number of scenarios at a particular sets will reduce from n to k. When it will reduce, you just completely you terminate your process. So, after removing a scenario, update the scenario set and recompute the distance again. Continue the removal process until the scenario set is reduced to a pre-specified number. Okay. So, what is clustering algorithm then? The clustering algorithm is based on the statistical similarity, where we will see again the statistical distance. The centroid of each cluster is used as a representative of the scenario. That means, you have 1000 samples, you made them cluster, you find the centroids for those cluster, and those scenarios which are more closer to that centroid, you cluster them together, and then you will get the number of reduced scenarios. Okay. Then you can reduce it to number of samples which is manageable, and this is 10 to 50. So, algorithm is that choose the number of clusters you actually want, that each cluster will give you the each reduced scenario value. That means, if you want 50 scenarios, you take 50 clusters. Okay. So, apply clustering algorithm. K means, let us say, on the full scenario set using appropriate distance matrix. That means, you calculate the Euclidean distance for K means clustering algorithm. Identify cluster centroids to represent each group. Okay. Assign probabilities to centroids based on the total probability mass of the corresponding cluster. That means, you cluster the similar points together at a point and you assign the probabilities of each and every point of that cluster to the centroid, and then you will get an equivalent representation of that cluster for your new scenario reduced scenario set. Use centroids and the updated probabilities in the reduced scenario set. Okay. For fast forward selection technique, it is same as your forward selection technique, but we did a greedy heuristic search for it, where based on probability weight and distance matrix. It is faster than the traditional fast forward selection, but can yield to near optimal reduction. That means, you can take some of the points which are not required, you take the redundant, and you will miss out some of the good solution representation or scenario representation. That is possible because you are doing it very fast. Steps: initialize again with an empty, then at each step compute the distance between each remaining scenario and those already selected. Add the scenario and reduces the total distance the most. Okay. Repeat until the desired number scenario is selected. It is same process, just you will do a heuristic search for it. Then the optimal scenario reduction techniques, which solves a mathematical optimization problem, which is the minimizing the distance between the reduced and the full scenario sets. So, you will minimize the Wasserstein distance, the total Wasserstein distance for that, and you will formulate that problem as a minimization objective function problem, and you will take the scenarios as a variable, your updated scenarios. So, yields globally optimal reduced set, but is computationally intensive because that will take time, and also you need to formulate the entire problem. So, that is a difficult problem. You have to formulate a constraint optimization problem to solve an optimization problem. So, that is computationally, obviously that is a very strenuous job. So, steps is that formulate the scenario reduction as a linear programming problem. Objective will be minimization of the chosen distance metric. Constraints ensure the reduced scenarios properly represent the original distribution. So, you have to fit your constraints also accordingly. Then solve the optimization to obtain the optimal subset of new probabilities. Okay. So, with this you will see that comparison between different method. So, you will see that for a forward selection, start point is an empty set, for backward is a full scenario, for k-means it is a random centroids, and forward selection, first forward selection also it is empty set, and optimal reduction is a full set. Forward selection, the criteria is the minimum distance gain, backward selection is the minimum distribution change, k-means clustering is the minimum within the cluster error, and fast forward selection and your optimal reduction is same as the greedy rule and the global distance minimizer. Obviously, your fast forward selection and your forward selection are very fast in nature because you are eliminating one by one. So, little bit of longer time you need for backward reduction technique. K-means clustering is also very fast because you have already decided the centroids and you are just adding the points who are closer to that centroid. So, it is very fast algorithm. The slowest algorithm is your optimal reduction because you have to formulate an MILP, and if you are going with let us say 100 scenarios, then you have to give 100 variables, and that is a big problem to solve. So, that is taking longer time. Accuracy is very high if you go for forward selection and as well as backward reduction. K-means clustering, if your centered choice is not good, then you will not get good accuracy. Okay. Fast forward selection also it is somehow good, but it is lesser than your forward selection. And optimal reduction you will get the optimal solution. So, that is most optimal solution, but the speed of that process is very slow. So, with this I will end today's lecture and we will continue with this probabilistic OPF in the next class. Thank you.